Alrighty, physics review video number 10. Static electricity. Here we go. Static electricity. Static means stopped. Electricity, electrons, they're stopped electrons. That doesn't happen. And so you get to absolute zero. So that doesn't really happen in most cases because most things are a little above absolute zero. So what is static electricity? You walk across a carpet with your slippers in the winter especially, and you build up a charge. You're building up energy. Static electricity is stored energy, or stopped energy in a way, stored up in electrons. They're ready to move, right? So if you look on your sheet, static electricity, you should think of that as stored energy in electrons. And electroscope, it detects a charge. Induction is close but not touching, and conduction is touching. You actually connect. So induction is when you come kind of close, but with conduction you connect. For instance, if you have an electroscope like one of these, like a little drum set thing, like we used in the lab, it has this holder here, and then it's got an indicator. That indicator would move if you had a negatively charged tube. This would be a plastic tube. Remember, we have a bunny. Go back to this. We got our bunny fur. It's apparently a bunny that's been too close to the nuclear power plant, and it's been really affected by that. Alright, okay, so here's our little bunny, get a little tail. The bunny gets a back rub, remember, from the plastic tube. It feels positive because it loses electrons, and this gains electrons. And now that's going to make this positive up here, even though it doesn't touch, so this is induction, that's going to make this negative down here, and like things repel each other. Opposites attract, right? That's why my beautiful wife is attracted to me. And then likes repel. That's the way God intended it. So we're looking at this, and only in this thing, only the electrons move. So now I'm looking at number 48. The electrons move down to the bottom. The protons were abandoned at the top. The electrons move from the bunny to here. The bunny didn't pick up protons. The bunny lost electrons. And you don't mess, if you look at number 48, you don't mess with the proton number. That's Mr. Grunn's little reminder right there, by the way. Number 49, you average out the amount of charge when objects touch and separate. For instance, if I have plus 6 coulombs, plus 2 coulombs, if these touch and separate, what's going to be the charge on each of them afterwards? So, anybody know? It's going to be plus 4. Because what you do is you add them up. So this plus this is plus 8 coulombs, but then they're each going to take half. So that gives you to this number right here. So there's your plus 4 coulombs. Remember, a coulomb is a boatload of electrons. 6.25 times 10 to the 18th elementary charges or electrons. And by the way, back to these guys right here, if these two are around each other, they would have an electric field, a force field. And electric fields obey pants. Pants is positive away, negative towards. So this electric field is going to go out in all directions. So like charges repel, we said. So the reason that is, or the way you can show that, I should say, is they're kind of pushing off of one another like that. Remember this? They kind of, almost like springs push off of one another. Number 50, pants for electric field. Force field lines never cross. Ants, which are magnetic field lines, which you know, I bet. Pants, none of them ever cross. The force equation, if you want to calculate something for this, I'll put it up here. It's Fe equals, what's the rest? That's right, Jimmy. I heard that. K, Q1, Q2 over R squared. And a couple things here. Remember, you can plug in actual numbers for this. Like if I double the charge, it's going to, and that's the only thing that changes, it'll double the force. If I double the distance, it'll be 111 over 2 squared, which will be 1/4 the force, if that's the only thing that changes. If I'm looking at graphs here, what would that graph look like? Inversely related. Okay. If I'm looking at another graph here, hopefully this will show up. Q1, okay, that'll be like that because they're directly related, no squared, and it's only one of the charges. Those have to do with some graphs on number 53, and I'll cover the rest of those in just one second. Capacitor example. A capacitor is that thing inside a camera. It's not only in cameras, but that's the main example, where you hear it going, and it's charging up to make the flash go. It's basically two metal plates, and remember it looks like an equal sign because all the points, like A, B, C, all the points in here have equal electric field strength, have equal force on an electric charge. If that's a positive plate and that's a negative plate, the electric field is going to go pants, positive away, negative toward. It's going to go right down there. It won't go through it, but it'll go from right one to the other. And so a capacitor has a constant electric field. And then the other graphs right here, real quick. E versus D from E equals V over D. That is like that. Another one, I did F versus R. E versus V. Because E equals V over D, directly related, what's it going to look like? Yeah, buddy, like that. And V equals W over Q. V, W, Volkswagen. The more energy you put into your voltage, the more it's going to soup it up. So that's going to be like that. Thank you very much.